This video describes or defines the term atomic radius and describes how a person could predict the relative radius of an element compared to other elements based on its position on the periodic table. Defining the term atomic radius is a little more difficult than you might imagine because atoms are not like, say, billiard balls. They're not rigid spheres. They have these electron clouds that are in constant motion, and the size of the electron cloud can depend on what other atoms are nearby, the particular atom, the radius of which we're trying to measure. So we've come up with a definition, a rough definition, that the atomic radius is half the distance between nuclei of two adjacent atoms. So if we take two sodium atoms, and we find their nuclei, and then measure the distance between those two nuclei, and then cut it in half, that's how we define the atomic radius. As it turns out, our periodic table is very nicely set up so that we can predict how big the atomic radius of an element is compared to other elements based on its position on the periodic table. So there are trends of atomic radii on the periodic table. So we need to know about the group trend, so what happens to the radius as you move down a column on the periodic table, and the period trend, so what happens as we move from left to right across the periodic table in terms of the element's atomic radii. We'll first explore what happens to the size of an element as we move down a group on the periodic table. And to look at that, we want to compare two elements. We'll look at lithium, which is in period 2 on the periodic table, and sodium, which is in period 3. So lithium's electron configuration, because it's in the S1 column, ends in 2s1, and sodium's electron configuration ends in 3s1. Also noteworthy is the fact that lithium has a total of 3 electrons. 2 of those electrons exist in the first energy level, and 1 exists in the second energy level. So if we were to draw a Bohr model of a lithium atom, it would look like the picture at the top of the screen. So we have the nucleus, that's in red, then the first energy level has 2 electrons in it, and then the second energy level has 1 electron in it, for a total of 3. Sodium has an atomic number of 11, so it has 11 electrons. It still only has 1 valence electron, but that valence electron is in the third energy level. So sodium has a nucleus, followed by 2 electrons in the first energy level, 8 in the second energy level, and then 1 in the third energy level. Looking at these two, it's pretty apparent that sodium is a larger atom than lithium because it has more energy levels filled with electrons. As you move down a group on the periodic table, the number of main energy levels filled with electrons increases with the period. So the trend is that atomic radii increase the farther down a group we are because more energy levels contain electrons. So to reiterate what we just said, as we move down a group on the periodic table, it doesn't matter which group, the elements get larger because higher energy levels are being filled with electrons. It's also important to note that there is a trend as one moves from left to right across the period of the periodic table. And to explore that, we'll look at the elements lithium. Lithium has 3 electrons and its electron configuration ends in 2s1, and beryllium, which has 4 electrons and an electron configuration that ends in 2s2. So if we were to draw Bohr models of lithium and beryllium, we would say that lithium has 3 electrons, 2 of which are in the first energy level and 1 of which is in the second energy level. And beryllium has 4 electrons, 2 of which are in the first energy level and 2 of which are in the second energy level. Looking at these two pictures, it's not readily apparent which one is larger than the other. They both have 2 energy levels that contain electrons. And in fact, if we were to go across period 2, we wouldn't see any additional energy levels filling with electrons. So all of the electrons that would be going into the elements in the second period would be going into the second energy level. So neon, the largest element in period 2, would have a nucleus, and then it would have the first energy level with 2 electrons, and the second energy level with 8 electrons, for a total of 10 electrons. So as we move across the period, we don't gain energy levels. However, if we look at data for atomic radii, we see that beryllium is actually smaller than lithium. So beryllium is smaller than lithium even though it has more electrons. And this is bothersome to students, for some students, because they think if you add electrons, the atom should be getting bigger. But in reality, if you're adding electrons to the same energy level, the atoms will actually get smaller, and we'll talk about why that is in a moment. To understand why it is that as we move from left to right across the periodic table, the elements get smaller, we have to understand that as we add electrons, we're adding them to the same energy level in a single period. So, for instance, in period 2, we're adding electrons to the second energy level only as we move from left to right. In addition to adding electrons, though, to the second energy level, we're also adding protons to the nucleus. The charge of the nucleus is called the nuclear charge, and the nuclear charge increases as we move from left to right across a period on the periodic table. The increase in nuclear charge increases the attraction of the outermost energy level of electrons, and so the outer energy level progressively becomes closer and closer and closer to the nucleus as the nucleus grows. This decrease in size is actually quite substantial, and so the elements on the right side of the periodic table are much smaller, in some cases half the size, of their corresponding elements on the left side of the periodic table in the same period. Another thing to keep in mind when considering the relative size of an atom is that while the nucleus is attracting the outermost energy level of electrons, the electrons on the innermost energy levels are repelling the outermost energy level electrons. This effect is called shielding and it's important to the size of the atom. The more shielding there is by innermost electrons on the outer electrons, the less effect the positive nucleus has on the outer electron. So the more shielding there is on the inner electrons, the larger the atom would be, because the outer electrons would be less attracted to the positive nucleus. As we move from left to right across the periodic table, we get more outer electrons in the outermost energy level, and so the inner electrons can't do as much shielding of each individual outer electron. So as we move from left to right across the periodic table, the shielding effect is reduced, so the outer electrons are more strongly attracted to the nucleus, and therefore the outer electrons are closer to the nucleus than in elements with fewer outer electrons. So if we were to summarize the periodic trends for atomic radius, we could say that as we move down a group, any group on the periodic table, the atomic radius increases because more energy levels are filled with electrons. We could also say that as we move across a period on the periodic table, the atoms get smaller in atomic radius, and they get smaller in atomic radius because the nucleus is growing in size as protons are added. The larger nucleus can more strongly attract the outermost electrons, bringing them closer to the nucleus and making the atom smaller overall. Also, electron repulsion by inner electrons is reduced as more outer electrons are added. So if we wanted to think about the largest element on the periodic table, we would try to remember the element francium. And then we could figure out the relative size of other elements based on remembering that francium is the largest. So in later videos, we'll talk about francium's other properties, and I want you to remember that francium is big, dumb, and ugly. So I want you to think of him kind of like the center on the football team, big, dumb, and ugly. And if you remember that, it's very helpful in remembering your periodic trends. So one thing that you might be asked to do on an exam is to look at a series of elements and put them in order from smallest to largest. And so if we pick a few elements, let's say we have calcium, barium, arsenic, and bismuth. If we were to put them in order from smallest to largest, if we know that francium is our largest element, and it's down here in the lower left-hand corner, if francium is the largest, as we move away from francium, the elements get smaller. So if we're trying to compare calcium to barium, we know that barium is larger than calcium because barium has more energy levels filled with electrons. So barium is larger than calcium. Similarly, bismuth is larger than arsenic. Bismuth is lower down on the periodic table and has more energy levels filled with electrons. And then as we move across the periodic table, if we wanted to compare, say, calcium and arsenic, calcium is larger than arsenic because arsenic has a larger nucleus. And similarly, barium is larger than bismuth. So if we were to put these elements in order from largest to smallest, barium would come first. Barium is the largest. And then we would have bismuth next because it has two more energy levels with electrons than calcium and arsenic. And then we would go back to calcium. And then the smallest element of those four would be arsenic. Another thing that you might be asked on an exam is to explain why one atom is larger than the other. So for instance, why is the atomic radius of strontium larger than that of magnesium? A response that students commonly give that is wrong would be to say that strontium is larger than magnesium because strontium is further down, group 2, on the periodic table, than calcium. That's an incorrect response. It is true that strontium is further down the periodic table than calcium is. However, you should consider that that's not actually the reason why. Strontium has been larger than magnesium. I'm sorry, I wrote calcium here. This should be magnesium. Strontium has been larger than calcium or magnesium since the beginning of time. The periodic table is a recent invention, and the periodic table was cleverly designed to reflect the reality that exists between different elements. We cannot use the periodic table to justify a trend. Instead, what we would say about strontium is that strontium has 4 energy levels that contain electrons. So that would be strontium. Strontium has 4 energy levels that contain electrons, whereas, let's see, magnesium has only 2 energy levels. So we have to go back to what's happening at the atomic level to explain a trend rather than talking about positions of elements on the periodic table.